What James Webb revealed is not that galaxies formed early, but that formation itself may not follow the order we assumed. For nearly a century, modern cosmology has rested on a quiet confidence in sequence. The universe begins hot and simple. It expands, cools, and slowly assembles complexity. First particles, then atoms, then darkness. Only much later do the first stars ignite, followed by galaxies that gradually grow, collide, and mature. This ordering is not a detail. It is the backbone of the standard cosmological model. Time in this picture is generous. It allows gravity to work patiently, chemistry to accumulate slowly, and structure to emerge step by step. The James Webb Space Telescope was built to look into that early darkness and confirm this story in finer detail. Instead, its first deep observations have done something far more unsettling. They have placed pressure on the sequence itself. According to the lambda cold dark matter model, the universe after the Big Bang entered a prolonged phase known as the Dark Ages. During this era, roughly the first few 100 million years, the cosmos should have been largely invisible. Neutral hydrogen-filled space, absorbing light rather than emitting it. No large galaxies should exist yet. Star formation should be sparse, inefficient, and localized. Heavy elements should be absent, because they require multiple generations of stars to forge them in their cores and scatter them through supernova explosions. In this framework, time is the limiting resource. You cannot build complexity without waiting. You cannot skip steps. Gravity needs time to pull matter together. Nuclear fusion needs time to process light elements into heavier ones. Galaxies, especially massive and orderly galaxies, are supposed to be late arrivals. James Webb looked precisely into this era. It targeted faint infrared light stretched by cosmic expansion light that left its sources when the universe was only a few % of its current age. What it found does not resemble a universe still learning how to exist. Webb's data reveal galaxies that are already large, bright, and structurally mature at redshifts above 10, corresponding to times as early as 300 million years after the Big Bang. Some of these objects, such as JADES GSZ130 and other candidates identified in the JADES and CERS surveys, appear to contain billions of stars. Their luminosities rival or exceed what standard models predict even for galaxies billions of years later. Their light is not weak or tentative. It is confident, organized, and chemically complex. This is where the crisis begins to sharpen. These galaxies are not merely early. They are early in ways that strain every step of the accepted timeline. To assemble billions of stars, a galaxy must first accumulate vast amounts of gas. That gas must cool efficiently, fragment, and collapse repeatedly. Massive stars must live and die, enriching the surrounding medium with heavier elements. Subsequent generations of stars must then form from that enriched material. Each of these stages consumes time. In lambda, cold, dark matter, there is simply not enough of it. The analogy often used is biological, because it captures the absurdity of the situation with uncomfortable clarity. Finding such galaxies at these epochs is like discovering a newborn with the skeletal density and bone structure of an elderly adult. It is not just advanced, it violates developmental order. Even more troubling is the chemical evidence. Spectral features suggest the presence of elements such as oxygen, neon, and possibly iron. These are not primordial elements. They are manufactured in stellar interiors and dispersed through violent stellar deaths. Their presence implies that multiple cycles of star formation and destruction have already occurred. But according to standard cosmic history, the universe at this time should barely be forming its first stars. This is not a marginal tension that can be resolved by adjusting a parameter or two. It is a compression of cosmic history so extreme that it begins to blur cause and effect. If heavy elements exist before there has been time to create them, then either our understanding of stellar evolution is incomplete, or the universe is operating under a different temporal rule than we assumed. One possible response is to argue that these galaxies are not as massive as they appear. Perhaps their light is boosted by unknown effects. Perhaps their stellar populations are unusual, dominated by short-lived, extremely massive stars. Perhaps dust properties differ in the early universe, altering luminosity estimates. Researchers are actively exploring these possibilities, but each proposed correction must work consistently across many independent observations. So far, the pattern persists. What makes the situation especially unsettling is not any single object, but the population as a whole. Webb is not finding one anomalous galaxy, it is finding many. The statistical weight matters. A few outliers could be dismissed. A population forces reconsideration. The phrase universe breakers has emerged informally among researchers not as a sensational label, but as a shorthand for the way these objects strain existing frameworks. They break expectations, not by being exotic in appearance, but by being too normal, too complete, too early. At a deeper level, the problem exposes an assumption that often goes unexamined, that cosmic time unfolds uniformly and sequentially everywhere. Lambda-cold dark matter assumes that structure formation is locally driven by gravity acting on initial density fluctuations, with no mechanism for coordination across vast distances. Yet Webb's early universe already appears organized. It shows large-scale coherence before gravity should have had the chance to produce it. If the universe truly began in a near-uniform state, and evolved solely through gradual amplification of small fluctuations, then early cosmic history should be messy and incomplete. Webb's images suggest something closer to readiness. Not chaos resolving into order, but order appearing with surprising immediacy. This raises an uncomfortable possibility. Perhaps the problem is not that galaxies formed early, but that formation itself is not strictly chronological. The assumption that cosmic evolution must proceed step by step may be an artifact of how we impose human intuition on time. If certain large-scale structures are encoded in initial conditions more strongly than we realized, then what looks like premature maturity may instead be rapid revelation. Another possibility is that the Dark Ages were not as dark as we believed. If star formation began earlier, and more efficiently driven by unknown cooling channels or exotic physics, then the early universe may have been luminous long before it was supposed to be. But this too requires mechanisms that go beyond the standard picture. What Webb has done is expose how tightly cosmology is bound to its assumptions about time. When those assumptions are stressed, everything downstream becomes uncertain. Galaxy formation, chemical enrichment, reionization, even the interpretation of cosmic background radiation depend on the same temporal scaffolding. It is important to be precise here. Webb has not proven that lambda-cold dark matter is false. Scientific frameworks rarely collapse overnight. But it has demonstrated that the model is incomplete in ways that matter. The universe Webb reveals does not feel like one slowly assembling itself from simplicity. It feels like one that reaches structural maturity with alarming speed. For decades, cosmologists have spoken of cosmic freedom. Matter expands into space. Structures emerge naturally. Nothing directs the process except gravity and chance. Webb's early universe challenges this comfort. It suggests constraints, patterns, and efficiencies that appear too effective for a system still in its infancy. If the universe is not as empty, not as passive, and not as temporally generous as we thought, then our language about cosmic evolution may need revision. The shock is not visual, Webb's images are beautiful, but beauty is not the problem. The shock lies in the quiet implication that the universe may not wait for time to do its work. The early universe no longer looks like a blank page slowly being written upon. It looks like a text that arrives already densely printed, leaving us to wonder not how it was written so quickly, but whether the writing ever followed the order we assumed. In the quiet logic of astrophysics, black holes are patient objects. They are born small, constrained by the deaths of massive stars, and they grow slowly limited, not by hunger but by physics itself. For decades, this understanding felt secure. Black holes could be extreme, even violent, but they were not reckless. They obeyed rules. They respected limits. At the center of that restraint lies a principle known as the Eddington limit. It is not an abstract idea. It is a balance point, a tug-of-war between gravity pulling matter inward and radiation pushing outward. As gas falls toward a black hole, it heats up. That heat produces light. That light exerts pressure. If too much matter tries to fall in too quickly, the radiation pressure becomes strong enough to blow the incoming material away. The black hole chokes on its own brightness. This limit sets a natural speed limit on growth. Even under ideal conditions, a black hole accreting continuously at the Eddington rate takes hundreds of millions of years to grow from a stellar remnant into a supermassive giant. The math is straightforward. The timescale is unavoidable. And for a long time, observations appeared to agree. Then, the James Webb Space Telescope began peering into the first few 100 million years after the Big Bang. And suddenly, the universe was filled with black holes that had no right to exist. In galaxies such as GNZ11, Webb has detected signatures of accreting black holes, with masses millions of times that of the Sun, shining brightly when the universe was still less than 500 million years old. According to conventional growth scenarios, there simply has not been enough time. Even starting from the most massive stellar remnants, even assuming uninterrupted feeding at the maximum allowed rate, these objects should still be small. Instead, they are already enormous. This alone would be troubling. But the situation becomes more severe with objects like LID 568. Observations indicate that this black hole is accreting matter at a rate roughly 40 times higher than the Eddington limit. Not slightly above, not marginally violating expectations, but overwhelmingly exceeding the balance point that was supposed to be enforced by radiation pressure. At such rates, standard physics predicts instability. The infalling gas should be blown away before it can cross the event horizon. Accretion disks should puff up and self-regulate. Feedback mechanisms should shut the process down. And yet Webb sees sustained luminosity consistent with a black hole that is feeding furiously and continuously. This presents a direct paradox. Either the Eddington limit is not as absolute as we believed under early universe conditions, or black holes in the primordial cosmos were growing through channels fundamentally different from those operating today. To understand why this matters, it helps to recall how black holes are thought to form in the first place. In the modern universe, stellar mass black holes are born when massive stars exhaust their nuclear fuel and collapse under their own gravity. The largest of these remnants might weigh tens of solar masses. From there, growth is incremental. Mergers are rare. Accretion is slow. Time is essential. But in the early universe, time appears to be in short supply. This has forced cosmologists to consider alternatives that were once regarded as exotic. One of the most serious candidates is known as direct collapse. The idea is deceptively simple. Instead of forming stars first, some regions of the early universe may have allowed enormous clouds of pristine hydrogen and helium to collapse directly into black holes, bypassing the stellar phase entirely. For this to happen, several conditions must align. The gas cloud must be massive, dense, and unusually warm, preventing it from fragmenting into stars. Molecular hydrogen, which cools gas efficiently and promotes star formation, must be suppressed. Under these circumstances, gravity can act unopposed, driving the entire cloud inward until it forms a black hole, with a mass of tens or hundreds of thousands of suns from the very beginning. Such a seed changes everything. A black hole, born already massive, does not need to violate the Eddington limit for long to reach supermassive scales. It only needs modest growth. The paradox shifts from one of impossible feeding rates to one of extraordinary initial conditions. And this is where the picture of the early universe begins to darken. Direct collapse does not occur in a calm environment. It requires intense radiation fields, violent inflows of gas, and the suppression of ordinary star formation. In other words, it implies a cosmos that was not gently assembling structure, but aggressively reorganizing matter on enormous scales. The universe we once imagined as quiet and simple in its youth begins to look turbulent and extreme. There are other possibilities as well. Some models suggest that early accretion disks were geometrically thick, allowing radiation to escape preferentially along certain directions, while matter continued to fall in along others. This anisotropic escape could weaken the effective Eddington limit without abolishing it entirely. Others propose that black holes grew in dense, chaotic environments where mergers were frequent and feedback inefficient. Yet each of these explanations carries a cost. They require conditions that are rare or absent in the local universe. They push physical processes to extremes, and they suggest that the rules governing black hole growth are not universal, but era-dependent. This is a profound shift. For much of modern astrophysics, the assumption has been that the same physics operates everywhere at all times. Gravity does not change its character. Radiation behaves consistently. Processes may vary in intensity, but not in kind. Webb's observations challenge that assumption, not by contradicting known laws, but by revealing regimes where their familiar outcomes no longer apply. There is also a deeper implication. Black holes are not merely endpoints. They are engines. As they accrete, they release enormous amounts of energy into their surroundings, heating gas, driving winds, and regulating star formation. In the early universe, rapidly growing black holes could have shaped their host galaxies almost from birth, shutting down star formation or triggering it in bursts. This feedback blurs the line between cause and consequence. Did galaxies grow massive because black holes formed early, or did black holes grow rapidly because galaxies assembled unusually fast? The clean sequence we once envisioned, stars first, black holes later, begins to unravel. What Webb has uncovered is not simply a population of oversized black holes. It is evidence that the early universe may have operated under a different growth logic altogether, one where collapse outran regulation, where feedback lagged behind inflow, where gravity briefly dominated before radiation could respond. Importantly, this does not mean physics was violated. It means physics was expressed under conditions we have never before observed, conditions that existed only briefly at cosmic dawn and left behind relics massive enough to be seen across 13 billion years of expansion. As observations continue, these black holes may yet find explanations within extended frameworks of known theory. But even now the message is clear. The early universe was not merely young, it was aggressive. It built extremes first and refined them later. If black holes could grow so quickly, if limits we once trusted could be bypassed or reshaped, then the early cosmos was not constrained in the way we imagined. It was capable of producing monsters almost immediately, and those monsters may have shaped everything that came after. The paradox, then, is not only about black holes eating too fast. It is about a universe that at its beginning seemed willing to abandon moderation entirely. In the standard story of the universe, light has a very specific origin. Stars shine because gravity squeezes their cores until nuclear fusion ignites. Hydrogen fuses into helium. Energy is released. Pressure pushes back against collapse. Balance is achieved. This mechanism is so fundamental that it feels inseparable from the idea of a star itself. But the early universe revealed by James Webb forces us to confront an uncomfortable possibility. Some of the first luminous objects appear far too bright, far too massive, and far too stable to be powered by fusion alone. They radiate with the energy output of billions of suns, yet they seem to exist at a time when ordinary stars should barely be able to form, let alone survive without collapsing into black holes. This contradiction points toward a different kind of engine, one that does not rely on nuclear reactions, one that does not require extreme compression, one that operates quietly and visibly through a component of the universe we have never directly seen. That engine may be dark matter. To understand why this idea matters, we need to step back to the conditions of the primordial cosmos. After the Big Bang, matter was almost entirely hydrogen and helium. There were no heavy elements. Cooling pathways were limited. Gas clouds struggled to shed heat efficiently. Under these conditions, gravitational collapse behaved differently than it does today. At the same time, dark matter dominated the mass budget of the universe. It did not emit light, it did not interact electromagnetically, but it shaped the gravitational landscape, forming dense halos that drew ordinary matter inward. Wherever the first structures assembled, dark matter was already there in overwhelming abundance. This overlap is crucial. If dark matter consists of particles capable of annihilating when they collide, such as WIMPs, weakly interacting massive particles, then regions of high dark matter density would have been sites of continuous energy release. Not explosive, not violent, but steady. A slow conversion of mass into heat taking place deep inside collapsing gas clouds. This is the foundation of the dark star hypothesis. A dark star is not dark because it emits no light. It is dark because its power source is invisible. Instead of nuclear fusion at its core, a dark star is supported by the annihilation of dark matter particles trapped by gravity. As these particles collide and destroy one another, they release energy that heats the surrounding gas. That heat changes everything. In an ordinary protostar, gravity compresses gas until temperatures soar and fusion ignites. If the object grows too massive, radiation pressure fails and collapse continues, often ending in a black hole. But in a dark star, the energy input arrives early and gently. The gas heats up before it becomes dense enough for fusion. Pressure rises without extreme compression. The object swells rather than collapses. The result is something unlike any star we observe today. Dark stars are predicted to be enormous. Not merely larger than the Sun, but larger than the orbit of Jupiter. Some models suggest radii of 10 astronomical units or more. Their surfaces are cool compared to fusion-powered stars, but their sheer size makes them extraordinarily luminous. Their total energy output could rival that of small galaxies. This provides a possible explanation for some of the baffling early light detected by Webb. Objects that appear too bright to be ordinary stellar populations, yet too stable to be short-lived explosions, could be massive dark stars shining steadily in the first few 100 million years of cosmic history. Crucially, this mechanism avoids an immediate collapse into black holes. Because dark stars are puffed up and diffuse, their central densities remain relatively low. Gravity is held in check not by fusion, but by continuous dark matter heating. As long as the supply of annihilating particles persists, the star remains stable. But this stability is temporary. Dark matter is not infinite. Over time, Annihilation depletes the local supply. As the fuel diminishes, the supporting heat weakens. The star begins to contract. Temperatures rise. If nuclear fusion ignites, the object may briefly resemble an ordinary star. But in many scenarios, contraction proceeds too quickly. The core collapses. Gravity wins. The end state is dramatic. A dark star can collapse directly into a massive black hole, bypassing the usual stellar death sequence entirely. If supermassive black holes existed astonishingly early, they required massive seeds. Dark stars provide a natural pathway. Instead of growing black holes slowly from stellar remnants, the universe may have produced enormous precursors that collapsed wholesale, delivering black holes weighing tens or hundreds of thousands of suns almost instantly. From there, ordinary accretion and mergers could build the giants Webb now observes. What makes this idea especially compelling is that it does not require new forces or exotic violations of physics. It relies only on the gravitational behavior of dark matter and the assumption that its particles can annihilate. Both are already embedded in mainstream cosmology. The novelty lies in recognizing that dark matter may have played an active thermal role in the early universe, not merely a structural one. There is also an observational subtlety here. Dark stars would not look like typical stars. Their spectra would be unusual, their surfaces cooler, their emission dominated by infrared wavelengths, precisely the regime where James Webb excels. Some of the brightest, strangest early objects detected so far fit this profile uncomfortably well. Of course, caution remains essential. Dark stars are still theoretical. No definitive example has been confirmed. Alternative explanations remain on the table. But the hypothesis exists for a reason. It addresses multiple anomalies at once: early brightness, rapid black hole formation, and the apparent absence of prolonged stellar buildup. It also reframes the early universe in a striking way. In this picture, the first light was not powered by fusion, the process that dominates cosmic history today. It was powered by something deeper and more elusive. The same substance that holds galaxies together may have briefly illuminated the cosmos before fading back into invisibility. If this is correct, then dark matter is not merely a passive background actor. It is a formative agent, a catalyst, a hidden participant in the earliest chapters of structure formation, and its influence may still echo through the universe in the form of the massive black holes that anchor galaxies today. There is a philosophical discomfort here as well. Much of astronomy is built on interpreting light. We infer structure, history, and composition from what we see. Dark stars invert that logic. They suggest that some of the most important processes in cosmic history were driven by something fundamentally unobservable, leaving only indirect traces behind. The universe in its youth may have been shaped by forces that shine briefly and then vanish, leaving us to reconstruct their existence from consequences rather than images. As Webb continues to refine our view of cosmic dawn, this possibility lingers. The first light may not have come from stars as we know them. It may have come from objects that no longer exist, powered by matter that barely interacts with the world we experience. And if that is true, then our understanding of how the universe lit itself for the first time is incomplete in a far deeper sense than we imagined. The glow that broke the darkness may have been fueled not by fusion, but by annihilation. In every standard picture of cosmic evolution, youth is loud. The early universe is supposed to be restless, crowded with collisions, bursts of star formation, violent rearrangements of gas and gravity. Galaxies, once they ignite, are expected to burn vigorously for long stretches of time, converting cold gas into stars with relentless efficiency. Silence in this framework belongs to old age. And yet James Webb has uncovered a population of galaxies that seem to have skipped that phase entirely. These objects are massive, well-structured, and unmistakably real. Their stellar populations indicate that they formed stars intensely, and then stopped. Not gradually, not after billions of years, but abruptly when the universe was only about 700 million years old. Astronomers have begun referring to them as sleeping beauty galaxies. The name sounds gentle, but the implication is severe. These are not faint dwarfs or failed structures. They are giants, and they appear to have shut down their internal activity far earlier than any existing model would predict. To understand why this is so disturbing, it helps to recall how galaxies normally die. In the modern universe, star formation ends slowly. Gas is consumed over billions of years, or heated by feedback from supernovae and central black holes. Environmental effects, such as interactions within clusters, strip gas away. The process is extended, messy, and uneven. Galaxies fade. They do not simply switch off. But Webb's observations suggest something else entirely in the early universe. These galaxies appear to have experienced a rapid rise and an equally rapid cessation. Their spectra show old stellar populations with little to no ongoing star formation. Their colors are red, not because of dust obscuration, but because massive blue stars have already lived and died. The analogy is unsettling. It is like encountering a young adult in perfect physical condition who suddenly exhibits all the biological markers of advanced age, without illness, without trauma, without warning. The timeline makes no sense. At 700 million years after the Big Bang, the universe should still be rich in cold gas. Dark matter halos are actively accreting material. Filaments of the cosmic web are feeding galaxies continuously. The conditions that sustain star formation should be abundant, not scarce, and yet in these systems the process has stopped. One possibility is simple exhaustion. Perhaps these galaxies burned through their fuel at an extraordinary rate, converting gas into stars so efficiently that nothing remained. But this explanation carries its own problems. To deplete such massive reservoirs of gas so quickly would require star formation rates far beyond what is typically observed, even in the most extreme starburst galaxies. Another possibility involves feedback. Rapidly growing black holes, like those discussed in the previous part, release enormous energy into their surroundings. Jets, winds, and radiation can heat or expel gas, preventing it from cooling and collapsing into new stars. In the local universe, this mechanism is thought to regulate galaxy growth. But in the early universe, the timing appears wrong. The shutdown occurs too soon, too thoroughly. If black hole feedback is responsible, it implies that these central engines reached maturity almost immediately and exerted control over their host galaxies before sustained star formation could proceed. That would require a level of coordination between galaxy assembly and black hole growth that strains conventional expectations. There is also the environment to consider. In dense regions, galaxies interact frequently. Gas can be stripped by tidal forces or heated by shocks. But Webb is finding quiescent galaxies even in locations where isolation should allow continued growth. The silence is not confined to crowded neighborhoods. This suggests that whatever mechanism halted star formation was internal, efficient, and decisive. At this stage, attention begins to move away from individual measurements and toward the patterns they form. Webb reveals a universe that assembles structure with surprising speed. Galaxies emerge early. Black holes gain mass rapidly. Light appears sooner than expected, and then another behavior comes into view. Systems that seem to halt their development just as abruptly. acceleration followed by suppression. That pairing is difficult to ignore. One interpretation is that the early universe possessed a form of self-regulation far stronger than we anticipated. Growth may not have been allowed to proceed unchecked once certain thresholds were reached. Mass density, energy output. Processes may have engaged that effectively capped further development. In modern cosmology, feedback is usually treated as a corrective mechanism. It smooths extremes over time, but the Sleeping Beauty galaxies hint at something more abrupt, almost binary, active or inactive, on or off. This raises an uncomfortable question. Are we observing a universe that enforces limits on complexity in certain regions? And if so, what determines where those limits apply? It is important to emphasize that nothing here requires intention or design. Physical systems can self-regulate without purpose. Stars balance gravity and pressure. Planets settle into stable orbits. Ecosystems stabilize through feedback loops. The concern is not motivation but efficiency. The shutdown observed by Webb appears too fast and too clean to fit comfortably within gradualist models. There is also a temporal dimension to this silence. Once star formation stops, it rarely restarts. Cold gas does not easily return. These galaxies may remain dormant for billions of years, essentially frozen snapshots of an early cosmic experiment that ended prematurely. If that is the case, then the early universe was not uniformly creative. It was selective. Some regions flourished briefly and then fell quiet. Others continued to grow. The cosmic landscape becomes patchy, uneven, governed by thresholds we do not yet fully understand. This realization forces a revision of how we think about opportunity in cosmic history. We often imagine the early universe as a fertile ground where everything was possible. Webb suggests a more constrained picture, a universe that experiments rapidly but also terminates outcomes just as quickly. There is a subtle but profound implication here. Star formation is not merely a physical process. It is the gateway to chemical complexity, planetary systems, and eventually biology. When galaxies fall silent early, entire potential futures are erased, not delayed, not rerouted, simply never realized. This does not imply tragedy in a human sense. The universe has no obligation to produce life, but it does suggest that the conditions we associate with abundance and growth may be rarer and more fragile than previously assumed. At this stage, explanations remain provisional. New data may reveal hidden reservoirs of gas. Revised models may reconcile rapid quenching with known physics. But even conservative interpretations acknowledge that these galaxies challenge the assumption that early cosmic history was uniformly energetic and unconstrained. The silence Webb has detected is not empty. It is structured. It is specific. It appears at a time when noise was expected. And that mismatch demands attention. As we step back and place these findings alongside early galaxy overgrowth, rapid black hole formation, and possible alternative energy sources, a coherent tension emerges. The early universe appears capable of extreme behavior in both directions. It can accelerate processes beyond expectation, and then halt them with equal decisiveness. That combination unsettles the comforting idea of smooth statistical evolution. It suggests that cosmic history may be punctuated by sharp transitions enforced by mechanisms we are only beginning to glimpse. The Sleeping Beauty galaxies do not shout. They do not blaze. They simply exist, massive and quiet, as reminders that growth in the universe is not guaranteed, even when conditions seem ideal. And as we absorb their presence, the question lingers: if entire galaxies could fall silent so early, What other constraints are woven into the fabric of cosmic evolution waiting to be noticed? At the largest scales imaginable, the universe is not scattered. It is arranged. Matter does not distribute itself randomly across space, but traces vast filaments, sheets, and nodes that stretch for hundreds of millions of light-years. This structure is known as the cosmic web. For decades, it has been one of the great successes of modern cosmology, a prediction confirmed by galaxy surveys and numerical simulations. Gravity, acting patiently over billions of years, pulls matter along, invisible scaffolds of dark matter, slowly weaving the universe into its present form. That story depends on time, a great deal of time. According to standard models, the cosmic web emerges gradually. Tiny density fluctuations, imprinted shortly after the Big Bang, grow under gravity. Filaments thicken. Nodes accumulate mass. Voids expand and empty out. The process is slow, hierarchical, and cumulative. Structure sharpens as the universe ages. James Webb, however, has begun to challenge the temporal order of that narrative. When Webb looks deep into cosmic history, it does not see a vague embryonic web struggling to take shape. It sees coherence, alignment, large-scale organization that appears surprisingly mature when the universe is still very young. The filaments are already present. The nodes are already populated. The voids are already defined. This is not merely a matter of visibility. Webb's infrared sensitivity allows it to detect galaxies embedded along filaments at redshifts where the universe is only a few 100 million years old, and what it finds is unsettling. The cosmic web appears not as a rough draft, but as a finished outline. The difficulty here is subtle but severe. Gravity alone is slow at large scales. Signals propagate at the speed of light. Matter responds locally. There is no mechanism within conventional physics for distant regions of the universe to coordinate their development rapidly. Each filament should grow independently, shaped only by nearby conditions, and yet the web appears globally consistent far earlier than expected. This leads to the first puzzle synchronization. Across immense distances, galaxies appear to evolve in correlated ways. Their orientations show unexpected alignments. Their spins exhibit coherence over scales that should be causally disconnected. Structures separated by hundreds of millions of light-years seem to share a developmental rhythm, as if responding to the same underlying pattern. This does not mean communication in the everyday sense. No signals are observed traveling faster than light, but it does raise a question about initial conditions. Were the seeds of structure somehow more tightly encoded than we assumed? Or is there a form of coupling at large scales that our models do not yet capture? In classical cosmology, information flows locally. Gravity transmits influence through space-time curvature. Radiation carries energy outward. Nothing coordinates behavior instantaneously across vast distances. The cosmic web was expected to reflect this locality: messy, uneven, statistically smooth but not synchronized. Webb's observations suggest something more organized. This is where the discussion begins to shift. From matter to information. The cosmic web is not just a distribution of mass. It is a pattern, a geometry, a network through which matter moves, accumulates, and evolves. When patterns appear earlier and more coherently than expected, it invites a different kind of question. Not only how matter moved, but how information about structure was encoded and preserved. Some researchers have begun to explore this idea, cautiously framing the cosmic web as an information-bearing system. In this view, the initial conditions of the universe may have contained far more structural information than a simple spectrum of random fluctuations. The web may not have emerged gradually from chaos, but unfolded from a highly constrained template. This does not require intention or design. Physical systems often store information implicitly. Crystal lattices encode symmetry. DNA encodes biological structure. Magnetic domains encode memory. The question is whether the early universe encoded large-scale structure more explicitly than we have assumed. Webb's observations of magnetic fields add another layer to this puzzle. Magnetic fields thread the cosmos. They are detected in galaxies, clusters, and intergalactic filaments. Their origin remains uncertain, but their presence is undeniable. In the early universe, Webb and other instruments are beginning to detect magnetic structures that appear remarkably organized, even before galaxies fully assemble. What makes this striking is not merely their existence, but their topology. The filamentary magnetic structures traced in simulations and observations resemble networked systems familiar from other domains, branching patterns, nodes of convergence, pathways of flow. The resemblance to neural networks is often remarked upon not as evidence of cognition, but as a reminder that certain geometries recur when systems optimize connectivity and transport. In the brain, networks emerge to efficiently transmit signals and integrate information. In the universe, filaments channel matter and energy. The similarity is structural, not functional. But structure matters. If magnetic fields and dark matter filaments formed early and coherently, they could have acted as organizing agents, guiding gas inflow and galaxy formation along predetermined routes. In this picture, galaxies do not merely fall into place. They follow paths already laid out by the geometry of the universe itself. This reframes the synchronization problem. Galaxies may not need to communicate with one another directly if they are all responding to the same underlying network. Their alignment and coordination would then reflect shared constraints, not exchanged signals. Still, the speed at which this network appears remains difficult to reconcile with gravitational growth alone. This has led some theorists to explore whether quantum effects could play a role at cosmological scales. Not through signaling, but through correlation. Quantum systems can exhibit long-range correlations, established at formation persisting without communication. If aspects of the early universe were quantum correlated on large scales, those correlations could later manifest as synchronized structure. Such ideas are speculative, but they arise from real tension in the data. Webb is not merely refining existing models, it is exposing regimes where those models feel incomplete. At this point, caution is essential. No observation demands that the cosmic web be intelligent, conscious, or directive. Those interpretations move beyond evidence. But the language of networks and information has become difficult to avoid because it captures what gravity-only descriptions struggle to express: early coherence, large-scale alignment, and persistent pattern. The cosmic web may be less like a random tangle and more like a pre-established framework, a system that constrains outcomes rather than reacting to them. If so, then cosmic evolution is not merely a process of accumulation, it is a process of unfolding. Matter flows along channels that already exist. Galaxies light up nodes that were defined long before stars ignited. Time does not create the structure so much as reveal it. This idea sits uneasily with the comforting notion of a universe that builds itself step by step. It suggests instead that large-scale order was present from the beginning, encoded in the geometry and fields of space-time itself. Webb's role, then, is not to show us how the web formed, but to show us how early it was already there. There is a quiet implication here. If the cosmic web emerged rapidly and coherently, then the universe may prioritize connectivity over randomness, flow over scatter, organization over entropy, at least in its formative stages. That does not violate thermodynamics. Entropy still increases, but it reminds us that entropy does not forbid structure. It allows it temporarily under the right conditions, and those conditions may have been present almost immediately. As this realization settles in, the cosmic web stops looking like a late-stage outcome and starts to resemble an operating system, not conscious, not purposeful, but foundational. A framework that governs how matter, energy, and possibly information move through the universe. And if the universe possesses such a framework, then many of the puzzles introduced earlier, rapid galaxy formation, oversized black holes, abrupt quenching, may be symptoms rather than anomalies, consequences of a deeper order that we are only beginning to perceive. The web does not speak, it does not decide, it does not observe, but it shapes everything. And James Webb, by looking far enough back, may have revealed that this shaping began almost at once. For most of its history, cosmology has been grounded in restraint. Even when confronting the unknown, the discipline has favored explanations that extend existing physics rather than abandon it. Anomalies were treated as gaps in knowledge, not invitations to rewrite reality. But as James Webb continues to map the distant universe with unprecedented clarity, a class of observations has emerged that resists comfortable categorization. They are not merely unexpected, they are unsettling in a more structural sense. These observations are not about brightness or mass or timing alone. They concern geometry. In multiple deep field surveys, Webb has revealed structures that appear unnervingly precise. Rings of matter arranged with near-perfect symmetry, filaments that maintain uniform thickness and curvature across distances where gravitational chaos should dominate, configurations that look less like the outcome of turbulent collapse and more like the result of deliberate placement. One such feature has been informally labeled the cosmic ring. At first glance, it resembles a gravitational lens, a foreground mass bending the light of a background object into a circle. But closer analysis reveals inconsistencies. The mass required to produce the observed symmetry does not align with the visible or inferred matter. The ring persists across wavelengths. Its geometry remains stable under modeling variations. It does not behave like an optical illusion. Another category involves what some researchers have called impossible filaments. These structures maintain coherence across scales where instabilities should fragment them. They curve smoothly without tapering branch, without losing uniformity, and intersect nodes at angles that minimize distortion. In simulations driven purely by gravity and hydrodynamics, such perfection is rare and transient. In Webb's data, it appears persistent. On their own, these features might be dismissed as statistical flukes or artifacts of projection, but their recurrence changes the tone of the discussion. Patterns repeat, symmetries cluster, and certain regions of space appear far more ordered than their surroundings, as if subject to different constraints. This has led to a provocative line of inquiry. What if parts of the universe are not merely evolving but being arranged? The phrase cosmic construction has begun circulating quietly, not as a declaration, but as a descriptive placeholder. It captures a pattern in which galaxies appear to occupy positions that optimize large-scale geometry, rather than emerge organically from random collapse. In these regions, matter seems less scattered and more staged. Importantly, this does not imply visible machinery or direct intervention. There are no tools, no moving parts, no obvious signatures of engineering in the conventional sense. The suggestion is subtler, that the underlying rules governing these regions may differ from those elsewhere, producing outcomes that resemble planning rather than accident. The most extreme example of this tension comes from a region provisionally labeled Paradox Zone Alpha. This area stands out not because it is bright or massive, but because it behaves inconsistently. Observations across multiple wavelengths suggest the simultaneous presence of matter and antimatter signatures without the expected annihilation signals. Under known physics, such coexistence should be brief and violent. Here it appears stable. Further complicating the picture, energy distributions within the zone do not conform to standard conservation expectations. Certain reactions appear suppressed. Others proceed without the usual byproducts. Time-dependent processes show irregular pacing as if local causality itself were distorted. It is tempting to label such findings as errors, instrumental noise, misinterpretation, calibration drift, and indeed, every effort is being made to rule those out. But as independent analyses converge, the anomalies persist. The region behaves as though the familiar rules of interaction are selectively relaxed. This raises a question that cosmology has long avoided. Are the laws of physics universally enforced, or can they be locally modified under certain conditions? In mainstream theory, the answer is clear. Laws are invariant. They do not flicker on and off. They do not bend around special locations. And yet Paradox Zone Alpha seems to function as an exception, not a breakdown but a compartment, a region where outcomes differ without chaos. One way to interpret this is through the lens of system management. Complex systems often contain protected zones, buffers, test environments, areas where rules are altered to explore stability or prevent failure. In computing such zones, isolate errors. In biology, membranes compartmentalize reactions. The concept is familiar, even if the scale here is unprecedented. This brings us to the most controversial suggestion of all cosmic maintenance. Across Webb's datasets, there are hints, subtle and rare, that certain structures appear to resist degradation. Distortions smooth out faster than expected. Density gradients stabilize instead of fragmenting. Features damaged by interactions recover their symmetry over time. Not dramatically, not universally, but often enough to be noticed. In classical physics, there is no repair mechanism at cosmic scales. Systems evolve toward disorder, perturbations propagate, structures decay unless actively supported. And yet in these regions, support appears implicit, not through force but through constraint, as if the permissible states of the system are narrowly defined and deviations are quietly suppressed. This is not evidence of intention, it is evidence of regulation. A regulated system does not need to be conscious. It does not need goals, it simply enforces boundaries. When variables drift outside acceptable ranges, feedback mechanisms restore balance. The early universe, as revealed by Webb, appears to possess such mechanisms in places where we did not expect them. Taken together, the implications are difficult to ignore. The cosmic web appears too coherent too early. Black holes grow too fast. Galaxies switch off too cleanly. And now certain regions exhibit geometry and behavior that resist stochastic explanation. One response is to assume we are still missing physics, that new fields, new symmetries, or new interactions will eventually account for everything. That is a reasonable stance, but it is no longer sufficient on its own. The anomalies are no longer isolated. They form a pattern. Another response is to ask whether the universe should be thought of less as a natural landscape and more as a structured environment. Not artificial in the sense of being built piece by piece, but artificial in the sense of being constrained, tuned, and monitored. This idea is deeply uncomfortable. It collides with centuries of scientific instinct, but discomfort is not disqualification. Science has advanced repeatedly by following evidence into territory that initially felt implausible. Still, caution is essential. No observation confirms the existence of an advanced civilization shaping the universe. No signal announces oversight. No artifact reveals authorship. What exists are patterns that strain purely emergent explanations. The language of construction, maintenance, and management is metaphorical, but it captures something real. The universe may operate as a system with global constraints that enforce order beyond what local interactions alone would produce. If that is true, then paradox zone alpha is not a flaw, it is a feature, a region where constraints differ, revealing the boundaries of the system itself. At this stage, we are no longer simply observing the universe. We are encountering its architecture, and architecture implies rules that were set before outcomes unfolded. Whether those rules arose naturally from deeper principles or were imposed by processes beyond our current understanding remains an open question. But James Webb has made one thing unavoidable. The universe is not only stranger than we imagined, it may be more organized than we are prepared to admit. For most of scientific history, the speed of light has been treated as a physical limit, a property of space-time itself. Nothing travels faster. No signal outruns it. Cause and effect remain bounded by its pace. This constraint sits at the heart of relativity, shaping how time, distance, and motion intertwine. It has been measured, tested, and trusted. Yet the deeper we look into the universe, the more this limit begins to resemble something else. Not just a speed, but a capacity. Not merely a boundary, but a throughput. In information theory, every system has a maximum rate at which it can process change. Computers have clock speeds. Networks have bandwidth. Displays have refresh rates. When complexity exceeds capacity, the system does not break. It constrains, it prioritizes, it updates incrementally. James Webb's observations invite an uncomfortable comparison. What if the speed of light is not only a feature of physics, but the maximum update rate of reality itself? This idea is not new, but it has rarely felt relevant to observation. Simulation theory has lived mostly in philosophy and speculative physics. It asks whether the universe could be described as a computational process, perhaps even implemented on a substrate beyond space-time. For a long time, the idea lacked traction because it offered no clear test. Webb changes that tone, not by proving simulation, but by exposing patterns that align unexpectedly well with information-based descriptions of reality. Consider first the cosmic microwave background. This radiation is the afterglow of the early universe, a near-uniform field of photons released when matter and light decoupled. Its tiny temperature fluctuations encode the seeds of all future structure. For decades, cosmologists have studied these fluctuations as statistical imprints of inflation. Recently, however, some analyses have highlighted something odd. When the CMB data are examined through the lens of information theory, certain correlations resemble error correction patterns. Not messages, not symbols, but redundancy structures. Relationships that suppress noise, preserve coherence, and stabilize global patterns against local disturbances. Error correction codes are not accidental. In engineered systems, they are introduced deliberately to maintain integrity when information is transmitted or stored in noisy environments. In quantum computing, they are essential. Without them, fragile quantum states decohere almost instantly. The suggestion here is not that the CMB contains a readable message. It is that its statistical structure behaves like a system designed to preserve information across extreme conditions. The early universe was hot, dense, and turbulent, and yet its large-scale correlations survived with remarkable fidelity. If space-time itself were a computational medium, such preservation would be necessary. This brings us back to the speed of light. In a simulated or computational universe, the maximum speed at which information can propagate is not arbitrary. It reflects the architecture of the system. A finite update rate ensures consistency. It prevents contradictions. It guarantees that no part of the simulation outruns the rest. From this perspective, light-speed causality looks less like a law imposed from within and more like a synchronization rule imposed from without. Every region of space updates in lockstep with its neighbors, constrained by a universal clock. This interpretation casts familiar relativistic effects in a new light: time dilation, length contraction, the relativity of simultaneity. All emerge naturally in systems where update rates are fixed and observers move relative to the processing grid. No paradoxes arise. The math remains unchanged. Only the interpretation shifts. The second anomaly Webb brings into focus concerns observation itself. In quantum mechanics, the observer effect is well known. Measurement alters outcomes. Wave functions collapse. Probabilities become facts. At microscopic scales, this is accepted. At cosmic scales, it has always seemed irrelevant. Telescopes do not disturb galaxies, or so we assumed. Yet Webb's long-term monitoring of certain galactic clusters has revealed something strange. In a small but statistically persistent set of observations, the activity of central black holes appears to change following periods of sustained observation. Accretion rates fluctuate. Jet emissions vary, not randomly but in ways that correlate with observation windows. No causal mechanism has been identified. The energy involved in observation is negligible. There is no physical interaction capable of producing such effects, and yet the correlation remains. In an information-based universe, this would not be surprising. Computational systems allocate resources dynamically. Regions that are queried more frequently may be rendered with higher fidelity. States may be resolved more precisely when inspected. This is not intention. It is optimization. Video game engines do this routinely. Only the visible environment is fully rendered. Distant regions are simplified. Details emerge when approached. The system conserves resources by responding to observation. The analogy is imperfect, but the parallel is difficult to ignore. If reality operates on finite computational capacity, observation could act as a trigger for state resolution, even at macroscopic scales. Not because the universe cares, but because it computes efficiently. The third and perhaps most radical clue lies in cosmic voids. Traditionally, voids are treated as empty, regions of low matter density, the spaces between filaments. But Webb's sensitivity has revealed that voids are not inert. They contain faint structures, subtle energy gradients, and weak but coherent field patterns. These patterns do not cluster matter. They do not form stars, but they persist. From a physical standpoint, this is puzzling. Why maintain structure where nothing happens? From a computational standpoint, it makes sense. Voids may function as processing space, memory, routing regions. In distributed computing, empty space is rarely empty. It is where information flows without interference, where signals propagate cleanly, where background processes run. If space-time itself is the hardware of a cosmic computer, then voids are not wasted volume. They are infrastructure. This reframes the cosmic web once again. Filaments channel matter. Nodes host computation-heavy processes like star formation and black hole accretion. Voids stabilize the system, maintaining coherence and preventing overload. In this picture, the universe does not simply exist. It executes. Of course, this language is metaphorical. No one is suggesting literal processes or code in the conventional sense, but information theory has taught us that physical systems and computational systems are deeply intertwined. Entropy, energy, and information are not separate domains. They are different expressions of the same underlying reality. When viewed through this lens, the speed of light emerges as a natural ceiling, a maximum rate of change, a bandwidth limit, not imposed arbitrarily but required for consistency. Without it, causality collapses. With it, the universe remains coherent. This also offers a new way to think about fine-tuning. Physical constants appear exquisitely balanced. Small changes would produce radically different universes. In a computational framework, this balance is not miraculous. It is necessary. Systems that are unstable do not run. Only parameter sets that permit long-term execution persist. The unsettling implication is that our universe may not be one of many random outcomes, but one of many viable configurations. Selected not for meaning, but for stability. None of this proves simulation. Every observation can still be interpreted within extended physical theory. New fields, new symmetries, new dynamics, but the convergence of clues, speed limits that resemble bandwidth, background radiation that behaves like error-corrected data, observation-dependent behavior, structured voids, pushes us toward a conceptual boundary. We are no longer asking only what the universe is made of. We are asking how it processes change. And once that question is on the table, the speed of light stops feeling like a wall. It starts to feel like a clock, a universal tick rate setting the rhythm of everything that happens. If that is true, then faster-than-light travel is not forbidden because it is dangerous or impossible. It is forbidden because it would break synchronization. It would introduce inconsistencies the system cannot resolve. The universe does not block such motion out of hostility. It blocks it out of necessity. Whether this framework reflects a literal simulation, a quantum computational substrate, or a deeper physical principle we have yet to name, remains unresolved. But James Webb has pushed us into a position where the language of information is no longer optional. It is becoming essential. And as we continue to observe, to measure, to query the universe more deeply, we may find that reality responds, not because it is aware, but because it is finite, structured, and operating within limits that feel increasingly familiar to anyone who has ever built a machine to compute. For a long time, planets were thought to be predictable outcomes of orderly systems. A star forms. A disk of gas and dust settles around it. Gravity sculpts that disk into planets that circle their parent sun in stable paths. Light provides energy. Warmth allows chemistry to proceed. Life, if it appears at all, is a fragile byproduct of balance. That picture has not survived contact with modern observation. James Webb has not only complicated our understanding of galaxies and stars, it has revealed that planets themselves often refuse to follow the script. Some exist without stars. Some endure conditions that should strip them bare. Others appear to host chemistry associated, at least on Earth, with biology, despite environments utterly unlike our own. The universe, it turns out, is far more permissive than we assumed. The first challenge to the traditional view comes from objects known as JUMBOs, Jupiter Mass Binary Objects. These are pairs of planetary mass bodies, comparable in size to Jupiter, drifting freely through space with no host star. They are not captured wanderers. They are not remnants of stellar collapse. They are born together, bound only to each other, moving through the galaxy as isolated systems. Under classical planetary formation theory, this should not happen. Planets form in disks around stars. Without a central mass to anchor material, there is no obvious mechanism to assemble objects of planetary size, let alone pairs that remain gravitationally bound. And yet, Webb and ground-based surveys continue to find them in abundance, particularly in young star-forming regions. Even more puzzling, some jumbos emit radio waves. Not thermal radiation, not reflected starlight, but coherent radio emissions that imply magnetic activity and internal energy sources. In the absence of stellar irradiation, something inside these worlds is generating and sustaining electromagnetic processes. One possibility is residual heat from formation. Another is tidal interaction between the paired bodies kneading their interiors and driving electrical currents. Either way, the implication is clear. Planets do not require stars to remain active. Energy can arise from motion, from gravity, from internal differentiation. This forces a re-evaluation of habitability. If planets can sustain energy budgets independent of starlight, then the traditional habitable zone, the narrow ring where liquid water can exist, loses its central importance. Life, if it emerges, may not care where a planet sits relative to a star. It may care only that energy gradients exist. The second challenge comes from planets that orbit stars far too closely to be considered stable, let alone hospitable. Consider 55 Cancri. This world orbits its star so tightly that its surface temperatures exceed the melting point of rock. Observations suggest vast oceans of magma. Its atmosphere is dominated by carbon monoxide, with little hydrogen or water. Any conventional notion of surface life seems impossible here. And yet the planet persists. Despite intense stellar radiation that should erode its atmosphere, 55 Cancri E continues to replenish it. Volcanic activity likely vents gases from the interior, replacing what is lost. The planet exists in a constant state of destruction and renewal, its surface reshaped continuously by heat and motion. This kind of world was once dismissed as a transient curiosity, but Webb suggests it may be common. Planets can survive in regimes that look, from a human perspective, uninhabitable. Stability does not require comfort. It requires equilibrium, however violent that equilibrium may be. The significance of such worlds is not that they host life as we know it. It is that they demonstrate how adaptable planetary systems can be. They expand the parameter space of what it means for a planet to exist at all. If planets can endure molten surfaces and corrosive atmospheres indefinitely, then biology, if sufficiently flexible, may find niches we have never imagined. The third and most provocative example involves a planet that appears, at least chemically, to brush against biology itself. K218b is a sub-Neptune-sized planet orbiting a red dwarf star. It lies in a region where temperatures could allow liquid water, but its size and composition differ markedly from Earth. It is likely enveloped by a thick atmosphere rich in hydrogen. Its surface, if one exists, may be buried beneath high-pressure oceans or exotic states of matter. Webb's spectroscopic observations of K218b's atmosphere have revealed something unexpected: the presence of dimethyl sulfide, or DMS. On Earth, DMS is produced almost exclusively by biological activity, particularly by marine microorganisms. There are no known abiotic processes that generate it in significant quantities under terrestrial conditions. This does not mean K218b hosts life. The planet's environment is alien. Its chemistry is not Earth-like. Unknown processes could exist that mimic biological signatures. Caution is essential, but the detection is enough to shift the conversation. For the first time, a molecule closely associated with life has been identified on a planet that is neither Earth-sized nor Earth-like. The implication is profound. Biology, if it arises elsewhere, may not resemble our own origins. It may not require continents, oxygen, or familiar oceans. It may operate under conditions we once dismissed as irrelevant. Taken together, these three cases, rogue planets, inferno worlds, and chemically intriguing sub-Neptunes, form a coherent challenge to anthropocentric assumptions. We have tended to define possibility in terms of our own experience. Webb is forcing us to define it in terms of physics instead. Where energy flows, where gradients persist, where chemistry can cycle, complexity may emerge. This reframes the search for life. It is no longer a hunt for Earth's twin. It is an exploration of viable systems, systems that maintain structure far from equilibrium, regardless of how strange they appear to us. There is also a broader implication for cosmic distribution. Rogue planets may be among the most common worlds in the galaxy. If so, then most planets do not orbit stars at all. They drift through interstellar space, warmed by internal heat, shielded by thick atmospheres or subsurface oceans. Such worlds would be dark to distant observers, nearly invisible unless they pass in front of background stars or reveal themselves through radio emission. They could host life entirely hidden from traditional astronomical surveys. In that sense, Webb's findings suggest that life, if it exists elsewhere, may be abundant yet difficult to detect. Not because it is rare, but because it does not announce itself in familiar ways. It may thrive in isolation, in darkness beneath ice or clouds, sustained by mechanisms unrelated to stellar warmth. This realization completes a thematic arc that has been unfolding across the previous parts. The universe builds structure rapidly. It regulates growth. It organizes matter along vast networks. And now it produces worlds that defy the environmental boundaries we once believed were essential. The lesson is not that life is guaranteed. It is that possibility is broader than expectation. If planets can exist without stars, remain active under relentless radiation, and exhibit chemistry suggestive of biology under alien conditions, then the universe is not narrowly tuned for rarity. It is tuned for variation. And in such a universe, silence is no longer evidence of absence. It may simply reflect that life does not always glow, orbit, or behave in ways we are accustomed to noticing. As James Webb continues to refine our view of these strange worlds, one conclusion becomes difficult to avoid. The question is no longer whether life could exist elsewhere. The question is how many forms it can take, and how many of them we have overlooked by assuming the universe must resemble us. For as long as cosmology has existed as a science, it has assumed a quiet boundary. The universe was everything that existed. Space expanded, time flowed forward, and all events unfolded within a single continuous arena. Even when that arena grew vast beyond comprehension, it remained singular. One universe, one history, one causal order. James Webb has begun to make that assumption feel fragile, not because it has discovered other universes directly, not because it has imaged alternate realities, but because it has revealed structures and events that behave as though our universe is not entirely sealed. The first hint comes from regions where gravity behaves as expected, matter behaves as expected, light behaves as expected. And yet something extra appears to be present. Lensing effects without sufficient mass, energy redistribution without local cause, distortions that do not match any known configuration of matter or dark matter. These anomalies are not random. They recur in specific environments. They appear at interfaces between large-scale structures. They cluster around zones already marked as unusual by earlier observations. To describe them, some researchers have adopted the cautious term dimensional bridges. These are not wormholes in the cinematic sense. There is no tunnel, no throat, no passage through which matter travels. Instead, they are inferred connections. Regions where space-time appears influenced by degrees of freedom not fully contained within our four-dimensional description. Gravity pulls from somewhere unseen. Energy seems to arrive without crossing space as we know it. In higher dimensional theories, such behavior is not forbidden. Models, inspired by string theory and brain cosmology, have long suggested that our universe may be embedded within a higher dimensional space. Other universes could exist nearby, separated not by distance but by dimensional orientation. Under most conditions, they would be invisible. Under extreme conditions, interactions could occur. James Webb's contribution is not to confirm these theories, but to make them feel less abstract. The anomalies it detects are precisely the kinds of effects such interactions would produce: subtle, indirect, gravitationally mediated, and resistant to ordinary explanation. The second line of evidence concerns time. In standard cosmology, time flows uniformly forward, locally distorted by gravity, but globally consistent. Events occur in sequence. Causality is preserved. Even when relativity complicates simultaneity, the underlying order remains intact. Webb has begun to observe events that strain this picture. Certain galactic collisions, starburst episodes, and black hole flaring events appear to unfold at rates inconsistent with their environments. Some processes complete far faster than models allow. Others seem delayed, as if time locally stretches or compresses beyond gravitational expectations. These discrepancies are not systematic errors. They persist across independent datasets. One interpretation is mundane, incomplete modeling. But when these timing anomalies coincide spatially with other structural irregularities, a different possibility emerges. Time itself may not be flowing uniformly across all layers of reality. This has led to the idea of temporal orchestration. In a multiverse framework, different universes need not share the same temporal rate. Time may pass faster in one, slower in another. If interactions occur, however weak, between these layers, events could appear desynchronized when observed from within a single frame. From our perspective, this would look like causality bending without breaking. Processes that should take billions of years complete rapidly. Events that should cascade quickly linger, not because physics has failed, but because multiple temporal regimes overlap. Webb does not observe time directly. It observes light, but light carries timestamps: spectral aging, energy loss, chemical maturity. When these indicators disagree, time becomes suspect. The third, and perhaps most visually striking anomaly, involves duplication. Across the deep field, surveys astronomers have identified pairs of galaxies that are within measurement uncertainty identical. Same morphology, same mass distribution, same spectral fingerprints, same apparent age, and yet they occupy different locations in space. Gravitational lensing can produce multiple images of the same object. That is well understood. But these cases do not behave like lenses. The geometry does not match. The lensing mass is absent or insufficient. The images persist across wavelengths and observational angles. Quantum mechanics allows for superposition, but only at microscopic scales. The idea that entire galaxies could exist in macroscopic quantum overlap has always been dismissed as impractical. Decoherence should destroy such states almost instantly. And yet here they are, or something that looks uncomfortably like them. One possibility is that these are projections, cross-sections of the same structure, intersecting our space-time in multiple locations. In higher dimensional geometry, this is not exotic. A single object passing through a lower dimensional space can appear multiple times. Another possibility is duplication across universes. Parallel structures evolving independently but constrained by similar initial conditions could produce near-identical outcomes. If weak coupling exists, their images might bleed into one another at boundary regions. In either case, the implication is the same. What we perceive as uniqueness may be local, not universal. Taken together, dimensional bridges, temporal anomalies, and structural duplication suggest that our universe may not be isolated. It may be one layer in a larger ensemble, and crucially, that ensemble may not be perfectly separated. This reframes the concept of limits. The speed of light discussed earlier may not merely limit motion within our universe. It may define the boundary of interaction. Information cannot propagate faster, because faster propagation would leak across layers, disrupting coherence. The limit protects separation. Similarly, cosmic horizons may not mark the edge of existence, but the edge of influence. Beyond them, other realities may exist, evolving under different conditions, occasionally brushing against ours at points of weakness or alignment. This idea is unsettling because it erodes finality. Events may not be entirely contained. Causes may not be entirely local. The universe becomes permeable, not in a dramatic way, but in a subtle, regulated manner. Importantly, none of this requires abandoning scientific discipline. These ideas arise not from imagination, but from attempts to reconcile observation with theory. When existing frameworks strain repeatedly in the same direction, expansion becomes reasonable. Still, caution remains essential. Alternative explanations are actively explored. Modified gravity, unknown forms of dark matter, early universe relic fields. The multiverse remains a hypothesis, not a conclusion. But the hypothesis now performs real work. It connects anomalies that otherwise remain isolated. It provides a language for discussing interactions that appear non-local, but not chaotic. It preserves physical law while loosening its domain. There is also a deeper philosophical implication. If our universe is one of many, then our physical constants, our arrow of time, our cosmic history are not inevitable. They are contingent. They arise from boundary conditions, not necessity. That does not diminish their significance. It reframes it. We do not occupy the center of existence. We occupy a viable layer, a region where conditions permit complexity, memory, and observation. Other regions may permit other things. James Webb was designed to look backward in time. It may also be showing us sideways, not by revealing other universes directly, but by exposing seams, points where the fabric of reality behaves as though stitched to something beyond itself. If these seams exist, then intrusion is not invasion, it is overlap. Not a breach, but a boundary condition expressing itself. At this stage, the most honest position is not certainty, but openness. The universe is behaving as though it is part of a larger structure. Whether that structure is best described as a multiverse, a higher dimensional space, or a deeper physical substrate remains unresolved. What Webb has done is make it difficult to insist that our universe is alone, self-contained, and complete. The boundaries we thought were absolute are beginning to look like interfaces. After everything James Webb has revealed, the question no longer sounds dramatic. It sounds technical. Why can nothing move faster than light? Why does every attempt to cross that boundary collapse into paradox or impossibility? Why does the universe appear vast, open, and expansive, is less than #0? 5# is greater than yet fundamentally closed. For a long time, the answer felt sufficient. The speed of light was treated as a property of space-time itself, a constant, a rule, something to accept, not interrogate too deeply. But Webb has changed the context in which that rule exists. What Webb sees at the farthest reaches of space is not chaos. It is not unfinished structure. It is not the turbulent residue of a system still assembling itself. Instead, the universe looks complete, not old but settled, not exhausted but stabilized. At the largest observable scales, matter distribution smooths out, energy gradients flatten, geometry converges toward uniformity. The universe does not fray at the edges, it resolves. This is the opposite of what many expected. If the universe were still fundamentally in flux, its boundaries should be messy, incomplete, transitional. But Webb's deepest observations suggest that the large-scale structure was established early and has been maintained with remarkable consistency ever since. That consistency invites a different interpretation. Perhaps the universe is not an open-ended process. Perhaps it is a completed system. In engineering, completed systems behave differently from evolving ones. They enforce limits. They protect integrity. They restrict access to internal states. They do not allow arbitrary intervention, because intervention destabilizes operation. From this perspective, the speed of light begins to resemble something familiar, a firewall. Not a barrier meant to imprison, but a constraint meant to preserve coherence. In computing, firewalls prevent data from entering or leaving at rates that would corrupt the system. In simulations, render limits prevent inconsistencies. In networks, bandwidth caps prevent collapse. Applied to the universe, the analogy becomes unsettlingly precise. If space-time is the medium through which reality updates itself, then allowing faster-than-light propagation would break synchronization. Events could outrun causality. Effects could precede causes. Local states could diverge from global consistency. The universe does not permit this, not because it is hostile to exploration, but because it cannot remain coherent otherwise. In that sense, faster-than-light travel is not forbidden. It is undefined. The system has no stable way to represent it. This interpretation also reframes the idea of cosmic completion. Completion does not mean static. It means bounded. The rules are not changing because they no longer need to. The architecture is already in place. This may explain why so many of Webb's discoveries point backward rather than forward. Galaxies form too early. Black holes grow too fast. Large-scale structure appears too organized too soon. The universe does not seem to be inventing itself gradually. It seems to be unfolding according to a pre-established framework. If that is true, then the universe was not under construction. It was under deployment. Time in this picture is not a builder. It is a revealer. This helps make sense of another deeply unsettling set of observations, causal loops. Across several astrophysical contexts, Webb has contributed to evidence that future conditions appear to influence earlier states. Not through signaling, but through constraint. Certain outcomes seem preferred, as though the system selects histories that remain globally consistent. In physics, this appears in solutions where boundary conditions at the future restrict allowable pasts. In quantum mechanics, it appears in time-symmetric formulations. In cosmology, it appears as fine-tuning that seems too precise to be accidental. If time were a simple line, this would be impossible. But if time is part of a closed logical structure, then loops are not errors. They are consistency conditions. In computation, this is common. Programs do not explore every possible path. They execute only paths that satisfy constraints. Invalid states are never realized. Seen this way, the universe does not evolve freely into all possibilities. It permits only those histories that do not break the system. That realization brings us to the final, most difficult implication. Why does such a system exist at all? One answer is purely physical. Perhaps deeper laws necessitate this structure. Perhaps reality can only exist as a bounded, self-consistent computation. That remains possible. But Webb's discoveries open another interpretation. Not as fact, but as framing. The universe allows complexity, but not arbitrarily. It accelerates structure formation, but caps growth. It supports life-friendly chemistry, but confines interaction. It permits observation, but limits manipulation. The system seems optimized not for expansion, but for development. This leads to the idea of a consciousness cultivation zone, not in a mystical sense, not as a declaration of purpose, but as a description of outcome, a region of reality in which observers can arise, persist, and reflect without destabilizing the environment that supports them. Physical constants are finely balanced. Too much gravity and stars burn out instantly. Too little and they never ignite. Too strong a force and chemistry collapses. Too weak and structure never forms. This balance has long puzzled physicists. Webb adds another layer. The balance appears maintained, not accidental. In a completed system, fine-tuning is not surprising. Systems that are not tuned do not persist. If consciousness arises only in systems that remain stable long enough to support memory, causality, and observation, then such systems will necessarily appear confined, not trapped, but protected. From inside, this protection feels like limitation. From outside, if such a perspective exists, it would look like containment. This does not mean we are prisoners. It means we are participants inside a structure that prioritizes coherence over freedom. The universe is not preventing us from leaving out of malice. It is preventing us from breaking it. That distinction matters. Exploration within the system remains vast. Knowledge within the system remains deep. Meaning within the system remains possible. What is restricted is not understanding, but escape. And perhaps that is intentional in the only sense that matters, intentional as a consequence of structure, not will. A completed universe does not invite modification. It invites comprehension. As James Webb continues to observe, it does not show us cracks to exploit. It shows us boundaries to understand. The farther we look, the clearer it becomes that reality is not unfinished business. It is a finished environment still being explored by those who live inside it. If this is correct, then the final question shifts. Not how do we get out, but what is this system designed to allow us to become? That answer is not written in the stars. It is written in us. In our capacity to observe, to reason, to question the very structure that contains us without destroying it. If the universe is a garden rather than a wilderness, then confinement is not punishment, it is cultivation. And the speed of light is not a wall. It is the fence that keeps the conditions just right for growth. If this long journey through the universe has brought you even a small sense of calm before sleep, I'm truly grateful you spent this time here with me. A gentle like or a quiet tap on subscribe is a simple way of letting me know these stories are worth continuing. And if you feel like it, I'd love to know where you're listening from, or any thoughts you'd like to share is less than #0. 5# is greater than your words, always help guide what comes next. Wishing you a peaceful night and a deep, restful sleep among the stars.